Hi class, welcome to the next section, chapter 8.5. Today we are going to talk about the average value of a function. This is a pretty short section and it's the end of chapter 8, our first sort of introduction to applications of integration. The next chapter we're going to look at more advanced methods of integrating, some more tips and tricks that we have. This section will show up again in chapter 10, where we visit more applications of integration after we've seen some of the more trickier methods of trying to approach integrals. So let's talk about the average value of a function. Okay, so the average value of a function is 1 over b minus a, the length of our interval of integration, multiplied times the integral from a to b over that interval, right? So 1 over the length. So again, you can kind of think of this as the area divided by the length, right? And so if you think about what an average is the sum of all the things that you have divided by the number of things that you have. And so here, remember that an integral is just a sum, right? It's the limit of a sum. So here we have a sum of things divided by the number of things that we have. So this should make sense at first glance that this is the average value of the function. So we have, the sum, the area under our curve divided by the length of our curve. So let's go ahead and start off with an example. So let's find the average value of the function f of t, that is e raised to the sine of t times cosine of t over the interval from 0 to pi over 2. So if we set this up, my b is pi over 2, okay? My a is 0, so the length of my interval is just pi over 2. And then I plug in my bounds, and then I have my function, okay? So here the easiest way to integrate this will probably be by making some sort of a substitution. U equals sine of t. Looks like it'll work because when I differentiate sine, I will get cosine, and so I'll get some sort of a e to the u du, okay, here. So if I pull out and I work on this value first, right, 1 over pi over 2 is the same as 2 over pi, right? The denominator of a denominator gets to move to the numerator. So make my substitution here. I'm going to let u be sine of t. When I differentiate that, I get d of u is the same as cosine of t. So remember, when you differentiate sine, the signs stay the same, right? SSS. Signs stay the same when I differentiate sine. So when I substitute this back in, I get e to the u du. U is very easy to integrate. It's just e to the u. Okay. Again, here notice that I'm keeping my bounds labeled as t so that I don't confuse myself and plug in u is 0 and u is pi over 2. So here I have my my integral, right? After I've integrated, I have my result. 2 over pi is e to the u. I'm in u, but my bounds are in t, so let's go ahead and substitute out back into the world of t. Here, I don't have to specify that I'm in t because we know how this bounding works here. So I am going to evaluate at pi over 2 and 0. When I plug in 0 for sine, I know that starts at 0, so that'll just give me 2 pi, right? This because e to the 0 is 1. When I plug in pi over 2, so just think about what sine does. It starts at 0 and it does a full cycle. So at pi, I'm back at 0, which means that halfway there, I am at 1. Okay, so I'm going to get 2 pi minus 1, right? So that'll be e to the 1 minus e to the 0 times 2 pi. And I can't simplify that any further. This is as far as I can go, right? So that would be my area, the exact area. So let's talk about the mean value for integrals. If you want, you can go back and look at the mean value theorem for integration. For differentiation. It'll help a little bit just because the form is the same. Okay, so for integrals, we have the conditions are if f is continuous on a closed interval from a to b, then there exists some value inside of that interval such that if I plug that value into my function, it will equal the average value of my function. So very, very similar to what we have for the mean value theorem for differentiation. However, this is for integrals, so it's slightly different because we have a different function here. Okay, so if I find there should be some value on this interval that if I plug it into my function, it will equal the average value of my function. Basically what this means is that my function takes on its average value somewhere along its interval of existence from one value to another. Okay. So if I move things around, I can move this b minus a around so it looks like this. So the integral of my function over a closed interval from a to b would be the same thing as some value inside of that interval evaluated at my function times the length of my interval. So if I exist from a to b, I have my function here. Okay, I'm looking at the area under my function. Somewhere inside of this interval, the height of my function is equal to the average value of my function. Okay, so let's go ahead and run an example. So find the value c such that when I plug this into my function, I get the average value of my function for the function x minus 3 squared over the closed interval 2 to 5. Okay. So if I set this up, I set up my function average. 5 minus 2 is 3. The integral is very, very simple, very basic, 2 to 5. And then my function, x minus 3 squared. This would be very, very easy to do with the u substitution or by expanding this out to its polynomial form. Let's go ahead and do in a substitution. So if u is x minus 3, when I differentiate this, I just get du is dx. Okay, very, very straightforward. So my integral for the average value becomes 1 over 3 u squared from 2 to 5 for x values, not for u values. I go ahead and this becomes u cubed. The reciprocal is 1/3, so I get 1 over 9. I evaluate this from x is 5 and x is 2, so let's go ahead and bring this back into x's. So we substitute back in x minus 3. And so if I plug in 5, this basically becomes 2 cubed, which is 8 over 9. And when I substitute in 2, I get a negative 1. So that's a negative 1/9. So a negative being subtracted is a positive. So I get 8 over 9 plus 1/9, which is just 9 over 9 or 1. Okay. So the function value is 1. So when I plug that in to my function, so again, right, my function value, my function average is 1. So my function at c, let's come back here. My function at c is 1, right? So if we plug 1 for the output from my function, I can then solve for the x that goes for it. So I'm going to take some value c, which is what I'm looking for. If you want to use x here, that's fine, but we're looking for a very specific value inside of this interval. So we can go c minus 3 cubed equals 1. Just go ahead and solve for that. So to break this down, we will first take the square root of both sides. Okay, so c minus 3 is plus or minus 1. I will add 3 to that. I get two different values, 2 and 4. So there's two values that this happens at. It happens at on the edge of my interval, and it happens somewhere in the middle as well. Okay? That's it. Like I said, very short section, less than 10 minutes for the video. For those of you who are in my class, you most likely have an exam after this, so good luck on that. For those of you who are watching just to watch and catch up or get ahead, I will see you on the video section for chapter 9.